Hi, I'm Professor Goins, and welcome to the Math Professor's YouTube channel. If you find the content useful or interesting, please consider subscribing. Also, we would appreciate any likes, comments, or sharing of our videos. All those free things will help us to grow and to reach more people, which we would sincerely appreciate. Let's go ahead and get into the video. I want to talk about the mean value theorem. First and foremost, let's consider the following sketch. I have this graph of this red curve. Now, if I look at a specific interval from A to B of this, so I just take, whatever the graph is, I just take a specific portion of it, and let's say it looks sort of like this. I can draw this secant line between the endpoints, and remember, a secant line is just a line that passes through 2 points on a graph. If I take these two endpoints, draw that secant line, it seems reasonable, based on the picture, that I could find somewhere along this curve, I could find a tangent line that's parallel to it. Now, in this case, there's going to be multiple, but in particular, I can find a tangent line that is going to be parallel to the secant line. Well, that is, the slope of the tangent line equals the slope of the secant line. What's another way we can write that? Of course, the slope of the tangent line is the derivative evaluated at this input, meaning this would be f prime of c is equal to the slope of the secant line. Well, remember, the slope of the secant line is rise over run. In other words, it's going to be the change in the y values divided by the change in the x values. Of course, the change in the y values, y value here would be the function evaluated at b minus the function evaluated at a, all divided by b minus a. And this right here is the standard equation that you will see represented in your textbook for the mean value theorem. There's another way that we can write that a little bit more formally, is I can write f prime of c. Of course, this is the derivative. Vertical bar means evaluation, so the derivative evaluated at x is equal to c, and the slope of the secant line is the average rate of change over the interval from A to B. Slightly more formal way to write it. Of course, all three of these are saying the exact same thing, just in different notation. If I look at the one in the bottom here, what does this say? The average rate of change over the interval is equal to the instantaneous rate of change at a specific point. So the average rate of change does actually occur at a certain point on the graph. Okay. So that's the statement for the mean value theorem. Now, what are the requirements on the functions in order for the mean value theorem to apply? Let's look at the following three cases. If I do a similar picture where I draw my secant line through the endpoints, and let's say I was going to sketch where the tangent line would be parallel. Well, suppose it would be parallel here, however, the point of tangency is not a point on the graph. Well, then there isn't a point where the tangent line would be parallel. Same thing here. What if I draw my secant line here, but that actually isn't a point on the graph? Then, maybe my graph, well, it could have a variety of situations, but let's just leave it as this right now. The secant line, doesn't pass through 2 points on the graph, so this isn't a secant line. Therefore, the idea is it must be continuous on the closed interval from A to B. So whatever I pick for my endpoints A and B, the function must be continuous on the closed and bounded region from A to B. It also must be, let's go over to this one, and let's say I was to put a secant line, so it is continuous in this case. Well, where would there be a point where it is, or where there's going to be a tangent line that is parallel to this? Well, if I think of this is a straight line and this is a straight line, then it's nowhere on there, nowhere on here. And this point right here is a corner, so it's not even differentiable there, which means there isn't a tangent line that I could put in that spot. So there's nowhere along this graph where I would have a tangent line that's parallel to this. So here are the two requirements. We must have continuity on the closed bounded interval, and we must be differentiable on the interior of that, meaning the open interval from A to B. And it should make sense that it has to be the open interval, because if this was the only graph that I had, right, the graph could continue. Let's go back to this one. The graph could continue past this, but what if I just stop it there? Then there's not going to be a tangent line. We could have, say, a left-hand derivative here and a right-hand derivative there, but the idea is the C value is going to be between A and B. So it must be on the interior. It must be somewhere between A and B. So this is the same thing here, as it must be between A and B. Now, we'll do a couple different computations with this, but just first and foremost, one of the most important uses of the mean value theorem is improving the fundamental theorem of calculus part 2, and that's a little bit beyond the scope of what you would do in your Calc 1 course, although the proof would be in the textbook. You could reasonably read through it and kind of see where this is used in there, but that is like the main sort of theoretical application of it is improving one part of the fundamental theorem of calculus. What you'll see in your calc course, however, will be questions like this, where you'd be given, say, this function here, the red graph, you'd be given that function, you'd be given the endpoints, and you'd be asked something along the lines of find the C value corresponding to the mean value theorem, or perhaps find the equation of the tangent line, and then sketch the graph to make sure that they're actually parallel. So something along those lines. So let's take a look at something like that. Let's take the following quadratic on the interval from -1 to 2. Of course, notice this is, of course, continuous and differentiable everywhere. In particular, continuous on the closed interval, differentiable on the open interval. Find the tangent line, which is parallel to the secant line. All right. Real quick sketch, so we know exactly what we're after. If I draw the parabola from -1 to 2, looks something like this. Of course, this would be -1, and this, of course, would be 2, and we have the secant line between these 2 points. So there's the secant line. Now we could ballpark it and say, well, where will I have a tangent line that's parallel? So let's just kind of ballpark it first to see if it's going to be reasonable when we get our final answer. Certainly not up here, certainly not back here, and you're probably looking right about there. Okay, so in other words, whatever this x value would be. Now, of course, this was a quick sketch. It's not really perhaps to scale. If this is over 2, that's up 2. So again, that should be a little steeper, but it is a quick sketch. But anyway, it should be about right here. On this rough scale, this would be 1. So maybe about a half would be approximately where that would be. But again, this is a rough estimate. What I'm going to do is I'm going to set up this equation and solve for it. Okay? So I'm going to set up f prime of c is equal to f of b minus f of a all over b minus a. F prime of c, so in other words, take the derivative of the function and then plug in c. Of course, the derivative using the power rule of x squared would be 2x. Plug c into that, that means the derivative would be 2c. On the other side, f of b minus f of a. F of b, remember in this case a and b are -1 and 2. Therefore f of b would be the function value at 2, which would be 2 squared, of course, which is 4, minus f of a means plug -1 in. -1 squared would be +1, so this would be 4 minus 1 over, and then b minus a. That would be 2 minus -1, which would be 3 over 3, which of course is 1. So I have 2c is equal to 1, which of course means that c, put this up at the top of the other side of the whiteboard after I clean it up. But I do get c equal to a half, which again is what we thought was going to be reasonable, somewhere in that ballpark. Make sure this is dry. Let's summarize what we found. I've got 2c is equal to 1, which of course means that c is a half. Now for the equation of the tangent line. So the equation of the tangent line right? So just like with any other line, I need a point and I need a slope. Well, the tangent line that we're trying to find is, of course, parallel to the secant line, and the secant line has slope 1. That means that the slope of the tangent line is 1. And where does that occur? Well, it occurs when the c value, or in other words, the x value, is 1/2, meaning the point of tangency would occur at 1/2, comma, the function value of a half, which would be 1/2, comma, a half squared, which is a quarter. So there's my slope and there's my point of tangency. Then my equation of the line, y minus a quarter would be 1 times x minus a half, y minus a quarter, x minus a half. Therefore, the tangent line would be x plus 1/2. Oh, no, minus a half. Minus a half, and then add a quarter, that would be x minus a half. And of course, that should make sense because the tangent line, if it's here, the y-intercept, of course, would be negative. Okay, so there's the equation of a tangent line for that parabola. All right, let's take a look at one more example. Let me see, clean this other side up. Let's see, I might just need the top half. Okay. For example, find the C value. And it looks like I didn't draw that well enough. Find the C value from the mean value theorem for the function f of x is equal to, let's see, so we did a quadratic, so let's not do a polynomial. Let's do a logarithm. Let's do the natural log of x on the interval from, let's say, 1/2 to 2. Okay, so find the C value from the mean value theorem for the natural log function on the interval from 1/2 to 2. Okay. Solution. Once again, we set up the following. Okay, the derivative is equal to the slope of the secant line. Of course, the derivative of the natural log is the reciprocal of the argument. And then plug in c, that would give me 1/c is equal to, now if I plug in again, this is a, this is b, that would be the natural log of 2 minus the natural log of 1/2 over 2 minus 1/2. Okay. And 1/2, remember, is 2 to the negative 1. Two minus 1/2 would be 3/2. Then I would have 1/c is equal to, well, a couple of things here. I'm going to do something with the numerator and the denominator. Exponents inside of logarithms can be brought outside as coefficients, meaning this would be the natural log of 2 plus the natural log of 2. And then if I divide by 3/2, that would be the same thing as multiplying by the reciprocal, so multiplying by 2/3. Here I'd have log 2 plus log 2, which is 2 log 2, multiplied by 2, which would be 4 log 2, and then over 3. So 1/c is 4 log 2 over 3, and then if I just cross multiply here, I would get the value of c to be 3/4 natural log of 2. A little bit of a messier number in the end, but again, conceptually it's the same thing. This is where this point on the graph is where the average rate of change, the instantaneous rate of change, would equal the average rate of change at this c value, which is between 1/2 and 2. Okay, thanks for watching. Don't forget to subscribe.